potential and so first we'll start with electrostatic potential. Now, what is electrostatic potential? Any idea?
Sir, electrostatic potential is the amount of work done to accelerate a charge from a reference point, like from outside of an electric field into the electric field.
Yes. That is electric potential and potential difference. Same thing, just between two potentials. So electrostatic potential means so work done to move a charge or bring a charge or unit positive charge from infinity to point. So V equals to W by Q naught. So unit will be, what will be unit here? Make the unit. If you don't know, still go with the formula. Chandana, what will be unit for V?
It will be volts.
Yeah, that is true. But what about here with the formula? What is other unit? What is work done? Unit of work done? Unit of work done? Joules.
Joules per
Yeah,
coulomb.
coulomb. Or as you said, volt. Now, this will be scalar quantity because work is scalar, charge is scalar. So it is scalar quantity. So electrostatic potential means what? Work done to move a unit positive charge from infinity to a point. So work done in moving that charge, that is electric potential. Now potential difference means if we say battery here, so work done to move a charge from one point to another point, or one potential to another potential. That is electrostatic potential difference. Now, electric potential at any point will be V equals to negative this electric potential and potential difference, or we can say electric field and this electric potential are always in opposite direction. So minus integral of E dr. We will say something somewhere from this point to infinity point, point P to infinity point, plus 1C, 1 coulomb, or 1 Q plus Q, or whatever you can say. So varies from infinity point to distance r. So potential due to point charge. Potential due to point charge, like this, the point here, due to that is, what was E here? K Q by R square. So what was K? 1 by 4 pi epsilon naught. And Q by R square here and dr here. This means you will get one more R. If you integrate this one, you will get ER. So this will give you 1 by 4 pi epsilon naught Q by R. Are you following what I'm saying?
Yes,
Yes.
I'm.
Okay. Now, see, if we have two potential here, so instead of R, it will be R1 and R2. Suppose if we have two potential as A and uh, B, in this same, there is one Q charge. So this distance is RB, this distance is RA. So this formula will become V equals to, or VAB equals to VB minus VA. Now which is integral of A to B minus E dr. So E we know, but here common we have here Q. So let's take minus Q by 4 pi epsilon naught 1 by RB minus 1 by RA. That's it. Unit will be same. It won't change. Now same way, if you have third point also, same thing you will do. But here we have considered 2 points. Potential difference between 2 points. So, understood? Any question here?
No, sir.
Okay. So let's go next. Now potential due to, or let's say electric potential due to continuous charge. Nothing much here. See, now we will just move around here and there. Formula will be same, just little bit up and down. Okay. So nothing much here. Just we will take one strip for this one. We will take one strip on this one. some if we take circle here, if we take strip here, then this is your radius r, and this strip is at radius small r. That's it. And we are taking a point P here somewhere. So this we are taking a strip, then it will be dr, and then charge will be dq, total charge, dq. So potential over this one, nothing but same thing. See, dq by 4 pi epsilon naught r. So this will become limit. If we have some values here, we will have limit here. Then we will 1 by 4 pi epsilon naught will be constant here. Integration of dq. Same thing we are roaming around and down. Now, if it is this for one charge, if we have system of charge, then Q1 will become here dq instead of this one will have summation Q1 by R1 distance plus Q2 by R2 and so on. So it will become Qi by Ri. This is summation. So nothing big here. Then we'll see here potential energy. Of a system of charge. Yeah, by the way, last Sunday, you didn't give a test, Chandana?
So I didn't know the test was going on. Actually, I didn't notice the notification.
Even like we have discussed in the last itself that we'll have test.
Sorry,
So
sir.
I could attempt only the half of the test. Like I gave it at the last moment and it stopped.
Okay, but I said like after class you should just join test, right? Even I saw Aditi only did only 2 questions, 3 questions. Chandana, I was upset. Okay, so this is I don't like this thing. I don't like it. Don't skip test next time, okay?
Okay, sir.
I won't give much question. I'll just give 10 questions. Even after this one, like this question, you need to solve like okay after this, whenever it is, like tomorrow or day after tomorrow, solve and send me solution. This weekend, Friday, right? Tomorrow, Saturday. This Sunday, you need to sit and solve this question and send me. Don't forget. Okay. So energy, potential energy of a system of a charge. Now, potential energy is more means what? Like, see, potential energy is like conservative. It is also like same. This energy is also conservative, like gravitation, electrostatic, and all that. Okay. So in this one, potential energy means like how much work is done, means external work in short. We are just saying here work done to move a charge, but here we'll say potential energy means some external work required to move a charge or move from one point to another point or moving between 2 different points. So let's say some small, a little bit like a work done in bringing charge from one to another point. So what we'll do here, some point, suppose this is one point B here, it's coming from A here, something like that. So this can be moved this way or this way. There are two ways of going. So potential difference between them equals to work done externally by Q. Integration of B, no, limits from A to B minus E dr. So these are the positional vector. In this case, if we take a length here, suppose it will become dl. It doesn't matter, like it's just variables. Small length dl or small length dr, whatever. So generally, R will take for distance. So here we'll take dl for length. Now, in this case, if we have two system of charge, then what we'll do? Total energy. We need to integrate here. Total energy of system will become work done into this charge here. So it will become 1 by 4 pi epsilon naught Q1 Q2 by R square. So total energy here. Now suppose if it is for dipole, obviously the charge will be same. What is dipole? Equal and opposite charges, right? Dipole is equal and opposite charges. So this will become kq square by r, or here r will be length of the dipole. Length of dipole means 2l generally we are taking. So kq square by 2l. So this small thing you need to remember. Okay, all this we won't, like, no need to write again and again. We already wrote in first chapter. So this is what same thing. And same next thing, same, like similar thing will come, like what charge per unit length, charge per unit area, and all that. Circular ring, all that. We'll see that which is required here. That is circular ring and all equivalent surface. So first, let's start with equipotential surface. So will you remember different ways of using these formulas? If okay, let's see here. Like suppose let's write some key points so that you don't have to keep in memory. You have to keep in memory so that it will be useful. Now for system of two charges, like as I wrote before, that's what same thing I'm writing, whatever I wrote. Just in like simple ways. Two charges. So U for system is negative. So net force will be attraction or attractive. Net force will be attractive in nature. Now, if U of system is positive, then net force is repulsive. Then U of system is maximum, means unstable. Unstable equilibrium. Then U of system is minimum, means stable equilibrium. So as I wrote for net force here, so that we can write here maximum value, minimum value, if you remember. Whenever we have maximum, we'll differentiate with respect to 0. Or we will equate with to 0. Equals to 0 for maximum. Now next thing, if it is for dipole, you can keep numbering. Okay, 1, you can say 2, this is 3. For dipole, U will be k q square by 2l. 2l is the distance. So fourth one, work done when q is moved. Okay, so W equals to QV. So 1 electron volt. This is most important thing, the case conversion. 1 electron volt equals to 1 volt into 1.6 into 10 to power minus 19 coulomb. 1.6 into 10 to power minus 19 joules. 1 EV. This conversion is most important. You need to remember. You have to remember this one because you'll get so many places like EV. Not in this chapter, maybe in like what is that? Semiconductors. Semiconductor everywhere will use EV. So if you want to define this one, we can say like 1 electronic volt equals to 1.6 10 to the power minus 19 coulomb of charge move from one point to another point, which uses 1 voltage, or which moves across 1 voltage. That is 1 EV. Just for understanding, this thing they would ask, but we should know meaning so that we can apply wherever it's required. This is most important conversion. Put a star mark and memorize it. I'll ask you anyhow, anyway. Star conversion. Okay. Now what we were doing, about to do, equipotential surface, right? Yeah. Okay, fine. This points, any doubt? This 5, 6, how many points you wrote? Whatever, yeah. 5 points, any doubt? Anything you want to ask? Till now, any problem? Both of you?
No, sir.
Okay. Will you remember this conversion?
Yes, sir.
Yeah, sure.
Mm-hmm. Okay. So equipotential surface. So from name itself, you can understand it is what? Equipotential surface. What do you mean by equi? From name, just give me an idea of just from the name, equipotential. Equi means
Equal.
equal. So equipotential. Now combine this. What will the meaning? Yes, tell me. What will the meaning of like equipotential surface?
A
Surface.
region where every potential is same.
Exactly. Let's rephrase this. Instead of region, we'll say surface. Surface where potential at any point on this surface has the same value. Now, it is similar to your electric field lines also, some properties. So like as we said, cone surface is the same at any point. So even if we talk about electric field lines, and this equipotential surface, these both are like perpendicular. Okay, electric field lines and equipotential surface, they are perpendicular to each other. So as they are perpendicular and the same value of this one, that means there is no work done. No work done. Especially on equipotential surface. So no work done in moving charge from one point to another point for equipotential surface. But work is done when it is moved from equipotential surface to another surface. Okay, understand this two statement. I'm saying both statement different way. First one, what I said, there is no work done on the equipotential surface if it is moving from one point to another point on the equipotential surface. But work is done when it is moved from equipotential surface to another surface. But inside equipotential surface, it is zero. There are so many confusing questions they will ask with these things. That's why I'm repeating again and again so that it will fix in your mind. Next thing we can say here, even you can write in your own words to remember. So equipotent surface do not cut each other. Then similar to electric field lines, any other point you remember? Yeah, strength. More the density, or let's say higher the density, more the strength. Larger the field strength. Okay, know the points, right? Okay. And by the way, guys, do you have some vacation in your college? It started or it is about to start?
It's about to start from 1st May.
First May. Then I'll try to take class in the morning itself, so that whole day you can be free if you want to go evening somewhere. What about you, Channa?
They didn't confirm for us yet, sir. So maybe we may have or we may not have.
Let's see. If you also have, then we'll have it in morning, like somewhat 9 to 10.
Okay, sir.
Okay. So let's go for next topic. In not topic, next topic, but same topic, but some parts of it. Choto parts. Okay. So yeah, some formulas first we'll write, then we'll go for it. Potential due to various charge action. The first one, at some point, like axial point, we wrote for this one. Same thing we'll do here. Electric potential. Potential due to some point. some distance x. So v will be equal to k q by r. No, sorry, x. K q by x. The same way it is for ring, circular ring. So if I draw a circle here, if I just let me draw a shape. From this distance in x, radius of ring was r. Let's just put it out. So v equals to k by under root, this length will be r square plus x square. Then third one, this is ring, this is disk. Calculate this. Ring means it will be charged outside, means over the surface.
So your voice isn't clear.
Okay, now is it clear?
Yeah.
Oh, 1 second, I just missed. Yeah. So circular ring means outer surface, circular disc means throughout the surface. So it will be plus 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 everywhere. Now if I draw from the center point P, distance not r, again x, then this is the radius r, charge q. So charge, it will be distributed over the area. So charge per unit area will be sigma. Sigma by 2 epsilon naught r square plus x square minus x. This similar derivation like your electric field lines. Okay, then we'll do tomorrow about this torque and all that things. Torque, and then we'll start some questions, some easy question first. Then we'll see some other topic like capacitance and all that. Yeah, we'll see one by one. This chapter will go on like 4-5 days.
Okay, sure.
Okay, sir.
Okay.
Thank you.
Yeah. Bye bye.